Hello everyone. Today we are covering a topic from IGCSE Cambridge Physics, lesson Thermal Physics, topic Transfer of Thermal Energy, subtopic Conduction and Convection. Let's first look at what thermal conduction is. Thermal conduction mainly happens in solids. You will understand why after we learn about what conduction is and how conduction happens. Now, if you remember, in solids, particles are arranged in such a way that they are tightly packed together in an orderly manner. And what happens to particles when energy is provided or when energy is increased? They would want to move around. But think about the solid. Can solid particles just freely move around? No, because they are tightly packed together. So the only thing they can really do is vibrate. When more heat is applied, then these vibrations become more vigorous. This way, you can transfer heat energy from one end of a material to the other end of the material. So, the heat transfer through the vibration of particles is what we call conduction. What happens is, because the particles with more energy collide with the adjacent particles with much less energy, they cause the adjacent particles to vibrate even harder. So, through these vibrations, the vibration is passed on to the next particle. Then that particle passes the vibration to the next particle. Like this, we can transfer the heat from one end to another. And this heat transfer happens from hotter regions to colder regions. You can see this diagram and get a better understanding. At this right end of this material, we are providing heat, the hot end. These particles start vibrating because of the provided heat. This particle passes the vibration to this particle because when this is vibrating, it goes and knocks on this one. And then this one also starts vibrating. So on and so on, the vibration gets passed on to the next particle until this heat is carried to the next end. Now do you why solids are better conductors? Because if it was a liquid or a gas, passing the vibration is not easy because the particles are not close together. Since solid particles are packed very tightly close together, they can easily transfer the vibration from one particle to another. Now, as you have already understood, for thermal conduction to happen, particles must be very close together because then only vibrations can be passed on to the next adjacent particle. So that's why solids are a really good conductor. Let's look at fluids. Fluids are liquid and gases. Now, both liquid and gas particles, they are spaced far away from each other, unlike solids. Because of that, conduction is not as strong as it is in solids. Rather, it is very rare or very poor conduction that happens in liquids and gases, unlike solids. Now, when we talk about conductors, there are two ends to the spectrum. Solids with high thermal conductivity are known as thermal conductors, good thermal conductors. And then there are solids with poor thermal conductivity. They don't really carry heat as fast as the good thermal conductors. They are called insulators or poor thermal conductors. So the two ends, conductors and insulators. Conductors conduct heat very well, and insulators, they don't really conduct heat that well. We can carry out a simple experiment to understand the conductivity of several materials. To do this, we first need rods of different materials we want to test that are of the same dimensions. It's important that they're the same dimensions because the dimensions of the rod would be the control variable. In this diagram, you can see we're using gold, lead, aluminium, iron, copper, and silver as the testing materials. And all of these rods are the same thickness. And then we need to attach a drawing pin at the end of each of these rods with a little drop of wax. We keep one drop of candle wax, and then before it dries out, we attach the drawing pin. And we do that for all the rods we chose. Now, we take a container which has some rubber-lined holes on one side. And then we insert these rods, the other side of the rod that we didn't paste the drawing pin, into the container such that the same length is pushed into the container. Okay, so again, another control variable. The same length should be pushed into the container from the other side. Then we fill the container with boiling water, and as soon as we do that, we need to start the stopwatch. Then, after a while, you'll notice, little by little, the wax at the other end of these rods, of some of these rods, they start melting. Why? Because now, one side of the rod, it's submerged in boiling water. So that side is getting heated. And that heat is carried to this other end by conduction. So when conduction occurs, the end that is not exposed to boiling water starts heating up. Because of that, the wax starts melting. And how do you know which rod has the most conduction? The one that melts the wax first and drops the pin is the material with the best conductivity. For instance, if the copper drawing pin, the drawing pin that was attached to copper fell first, then copper here has the best conductivity. It's a good conductor. And then let's say the aluminium drawing pin fell last, then aluminium would have the worst conductivity out of these materials. Depending on how long it took for the drawing pin to fall, we can arrange these materials from most conductive to least conductive order. Now, an interesting fact is good conductors are always made out of metals. Most of the good conductors are metals. And we can generally say that metals are great heat conductors. Why could this be? This is because metals have delocalized electrons. What are delocalized electrons? These are the detached or free electrons that are in a metal material because of their metallic bond nature. And when there are delocalized electrons, when heat is provided, these electrons are able to vibrate fast and also travel around the material. And when it is traveling around the material, these electrons will knock on other particles and make them also vibrate faster. So in a metal, heat conduction is much faster because of these delocalized electrons. With that being said, the range of heat conductivity is very broad. As you can see in this diagram, copper is one of the best heat conductors, while rubber, although it's still solid, is a better insulator and not a good conductor. Now, we learned that conduction is mainly for solids. Liquids and gases, they don't really do so much of conduction. Then how does thermal energy transfer in liquids and gases? To answer this, we have convection. Convection occurs when particles with more thermal energy move and replace the particles that have less thermal energy. Now, just with this definition, you can already say particles needs to move from more thermal energy to less thermal energy space. If particles have to move, then can convection happen in solids? No, they can't, because in solids, particles cannot move, they can only vibrate. So for convection to occur, it has to be a liquid or gas, where particles can freely move around. Convection is more efficient than conduction because particles are actively moving. And you will learn that it also requires less energy than the next type of thermal energy transfer we are learning, which is radiation. Because of this, most of the transfer that happens in liquids and gas happens through convection. But how does this movement of particles happen? Now, when there are heated particles or hot particles, that means they gain more kinetic energy. And when they gain more kinetic energy, they would want to move further away from each other. They want to spread further apart. This is also known as thermal expansion. And when they move further apart, what happens? Volume increase. Is there any change in mass? Of course not. Nothing happens to the number of particles. So mass remains the same. Density is mass over volume. Mass remains the same and volume increased. So what happens to density? Density will decrease. So the hot particles, or that area with hot particles, will become less dense. And what about the cooler particles? Nothing really happened to the volume because they remain the same. Because of that, the cooler particles are now more dense than the hot particles. So the more dense particles will sink to the bottom. The cool particles, they would sink to the bottom. And the warm particles, which are now less dense, they would rise up. This is how particles in both gas and liquid move from hot to a cold place. To observe convection in liquids and gases, we will be looking at two experiments. First, let's look at the experiment for the convection in liquids. To do this experiment, we need potassium permanganate crystals, a large transparent beaker, and of course some water. We first have to fill the beaker with water and then provide a little bit of heat from the bottom of the beaker. And when you're heating it from the bottom, as you heat, you drop a few potassium permanganate crystals to the center of the beaker. And you will notice as you drop the potassium permanganate, usually what happens is the entire water container becomes purple eventually. But when you do this as you're heating, you will realize is that instead of the color spreading from bottom to top, this time the color will rise up from the middle and then it will sink back down from the two sides. This is a perfect illustration of the convection current. This is because when the water is heated from the bottom, the heated water rises up from the middle, and then the cool water at the top surface, they sink down because of convection. And this can be seen through the spreading of this color. Of course, eventually, in about a minute or so, the entire beaker of water will turn purple. Now let's have a look at the experiment to illustrate convection in gases. For this experiment, we need a box with a transparent front, two glass chimneys. Now these are essentially just cylindrical shaped glass vessels with the top and bottom open. One candle and a lighter or a matchbox to light up the candle, smoke matches, or an incense. Either one would work. First, we need to set up the experiment as this diagram here. We keep the box and the candle inside the box to one side of the box. And on top of the candle, we place one chimney. And next to that, we have the other chimney. So what happens is, the air inside this chimney on top of the candle would be hot air because of the candle. And then the next chimney would have cold air compared to the other one. So we have a hot air chimney and a cold air chimney. Now, we need to hold the smoke matches or the incense stick above the cold air chimney. Usually, when you light up an incense stick, what happens to the smoke? What will you observe? The smoke will rise up from the incense stick, right? But here, when you're doing this experiment, you will notice that the smoke won't rise up. It will go down instead of rising up. The smoke will go down the cold air chimney. And then it will rise back up from the hot air chimney. Why is this? Now, this is a perfect illustration of convection currents in gases. The cold air sinks to the bottom and replaces the hot air that is going up. This is why instead of the smoke going up from the smoke match or the incense stick, goes down the cold air chimney and goes up and comes up from the hot air chimney, illustrating the convection in gases. Now that we have covered the theory for this topic, let's have a look at a few past paper questions. A student suggests some uses for containers made from good thermoconductors and for containers made from poor thermoconductors. In which row are both suggested uses correct? Before we go into the answers, let's look at what a good thermoconductor and a poor thermoconductor is. In a good thermoconductor, heat should be able to transfer from one place to another fast. So, a good thermoconductor has fast heat transfer. So, what about a poor thermoconductor? It's the exact opposite. This would have a slow heat transfer. Okay? Now, let's look at the given answers. Keeping a cold liquid at a low temperature. If there's something cold and it is kept cold, what can you say about the heat transfer? Is it slow or fast? It has to be slow, right? So, keeping a cold liquid at low temperature or the temperature not really changing much indicates slow heat transfer. So, here they are talking about a poor thermal conductor. Same applies to the next answer, keeping a hot liquid at high temperature. Again, there's not much of a difference in the temperature because something hot is kept hot. This also indicates slow heat transfer. So here also, they're talking about a poor thermal conductor. Transferring thermal energy quickly from a hot liquid. Now, already in the answer, they've given it out. The transfer of thermal energy happens quickly. So, fast heat transfer means here they're talking about a good conductor. And finally, transferring thermal energy quickly to a cold liquid. Again, they're talking about fast heat transfer. Means this is also about a good thermal conductor. Now let's look at the correct combination. Of course, A and B are already out. It can only be a C or D. And now we need to match the poor thermal conductor. This is the statement out of C and D that talks about the poor thermal conductor, keeping a hot liquid at a high temperature. So the correct answer for this question should be answer D. A good thermal conductor transfers thermal energy quickly to a cold liquid. A poor thermal conductor keeps a hot liquid at a high temperature. Have a look at the answers. The answer is answer D. We will look at one more question. In a refrigerator, the cooling unit is placed at the top and it cools the air next to it. How does the density of the air change and what is the movement after cooling? All right. Now, they're talking about the density of the air and it's about air and also talking about the movement, which already gives out that here in this question, we are talking about convection. Now, in convection, the fluid moves from hot to cold because of the density difference. Here, cooling, not heating. Let's look at what happens to the air density when cooling occurs. So when cooling happens, this means the energy, the kinetic energy of particles reduce. When kinetic energy of the particles reduce, they want to move less. When they move less, they want to come close together. The particles come close together. And when the particles come close together, we call it contraction. And when contraction happens, what happens is that volume reduces. Density is mass over volume. Nothing happens to mass. Mass is the same. Volume reduces. When volume reduces, what happens to density? Density and volume, they're inversely proportional. So density increases. The density of the air next to the cooling unit increases. And when density increases, would the material sink or rise up? Always the high density thing, or the higher density particles in this case, they would sink, and the less dense particles would rise up. So the correct answer should be density increases and the particles, because of this, will move down. They would move down, density increases. Let's check if this is the case. Look at the question, the answers. The answer is answer 4. Density of the air increases and the air moves down, just as we predicted. With this, we have come to the end of the discussion of this topic. Thank you for listening.